Hello everyone. So what we do in today's class is quickly look at some of the foundations of cryptography which are essential to understand how security is implemented in internet. Hmm? So today's class is just a quick review or an overview of these cryptographic principles, and if you know something better than what I'm talking here, yeah, feel free to correct me. Okay, so if you look at what cryptography means, it is basically an art of writing or solving secret codes. But if you look at the modern cryptography that we are mostly interested here, so we are interested in using cryptographic primitives in addressing that major objectives for secure communication like confidentiality, integrity, authentication, non-repudiation, privacy, etc., etc. So the concept itself is very broad in nature, and what we are trying to do here is looking at what are the basic primitives of cryptography and using these as a tool for secure communication over internet. So we are not going to talk about how these cryptographic algorithms really work that you study when you do course on cryptography, cryptology, and other things, which involves number theory, discrete algorithms, and other things. So here our idea is how we can use this more like a black box for addressing internet security issues. So I will talk about what are all the algorithms that are out there, how we can use it as we go forward. But yeah, this is not a topic about explaining you how these algorithms really work and how strong and how secure are these algorithms. And all of you know about encryption and decryption. And if you talk about encryption, basically what we do is we take plain text, which is the one that you wanted to send in a confidential manner to the receiver. In this case, assume that Alice wants to send a message in a confidential manner to the Bob. So in general, we assume this has message M, which could be of arbitrary length. Since we are talking about communication systems where you use bit stream for sending the data across the network, so it is typically a binary stream. The one that is generated by applying cryptographic function, which is called as E, which is the encryption function, it generates the ciphertext on the plain text that you give it. So by applying the encryption algorithm or encryption function on the plain text M, you get the ciphertext. Here the ciphertext is also a binary string which may or may not be of same length like plain text. In general, it is same size. In the case of sending large messages, you may also want to do the padding, also you want to do some randomization. So at other
Sir,
end, yeah, please tell me.
sir, the slide is not full screen.
What about others? Can somebody else tell me, are you seeing it as full screen or not?
Full screen.
Full screen, sir.
Yeah, Hamad, that looks like some issue from your side.
Screen, sir.
Hmm?
No, okay, sir.
Okay. So what Bob has to do is Bob takes the encrypted message, which is called ciphertext, apply the decryption function on that to get back the plain text. We use the word cipher basically to mean the algorithm that is used for transforming the plain text to the ciphertext
नहीं
or the
मैं
vice
अभी
versa.
थोड़ी देर में निकल रहा हूँ.
I think all of you please mute. Yeah, please mute unless you want to speak out. Okay. Okay. What I was saying is we use the word cipher to basically mean about the algorithm or the function that is used for transforming either the plain text into ciphertext or the vice versa. So the word cipher is very generic in that way. And if you look at for these algorithms to work a very robust manner, we want this encryption and decryption functions should have some parameters where the parameter that you are trying to use is the key. That means in addition to the message M, you also wanted to use some secret key while you are doing this encryption and decryption function. So that is the meaning of key. Okay. Only the secret that we have here is the key, whereas the ciphers are considered as public knowledge. So it is quite interesting and very counterintuitive to understand this part. So what this statement basically says is the cryptographic algorithms that you use are known to everybody, but the confidentiality of the data that you wanted to transmit, that is entirely relying on the key which is supposed to be only known to the intended party, in this case Alice and Bob. So this is quite remarkable. By just keeping the secret, the key alone, and by revealing how the cryptographic algorithm works out, we can make sure that these algorithms stay in the domain for quite long, can be tested by various researchers to check whether they have any vulnerabilities or not. By just changing the key, we can use the same cipher again and again for encrypting or sending different data to other parties. If you also keep the cipher also as a secret, as soon as cipher is revealed at some time in future, what could happen is you are end up have to design new ciphers. Designing new ciphers takes a lot of time and also requires lots of efforts. That is the reason why all the cryptographic solution that you use have ciphers which are like a white box known to everybody. Only key is the one that has to be kept secret by the parties who wants to communicate. I hope this point is clear to all of you. If anybody wants to ask, yeah, please let me know. Okay, let's come back to the language of cryptography. If you look at this illustration here, Alice has plain text, and using this encryption algorithm, by using the encryption key of the Alice, that is called K here, and she is encrypting the message and generating the ciphertext. So when the message is received by Bob, by applying the message to the decryption algorithm using the decryption key that Bob is having, that let's call it as KB. So Bob is able to get back the plain text that was sent by Alice. Where here we use M to represent plain text. Ka of M gives you ciphertext by encrypting the message with key that is owned by Alice. By applying KB on the ciphertext, we are getting back the plain text again. So it is at very high level. I'll come back and talk about how this is achieved in the context of both symmetric key cryptography and asymmetric key cryptography. Okay, but at the high level, so I can assume that there are two keys. That means each party is having their own keys using which I think somebody is having some messages which I'm unable to read. Can somebody help me understand what is the thing? Are you trying to ask me, or say I cannot read your messages while I'm speaking out here, unless who is that?
Sir, it's a message from Shubham saying in some cases even the cipher is a secret, like in critical applications like military.
So in some cases, ciphertext is also kept as secret.
I think he meant the algorithm, the cipher
I
itself
think,
is secret.
sir, I mean to say about the cipher algorithm actually.
Okay, okay. So you are talking about the cipher algorithm. See, again, you are right, Shubham. See, yeah, once in the early days, even the algorithms were also kept as secret. Uh, yes, you have the algorithm that is secret, and also key is also kept as secret. And yeah, so that will give you the best security that you can imagine. But the problem that researchers have found over the years is sometime or later the algorithm will be known to the attackers by some means. In that case, what you also have to worry about is designing new cipher algorithm that could be quite time consuming process. Yes, you would like to do that, but in the context of network security, where we are talking about the modern cryptography, we only rely on keeping the key as the secret and let everybody look at what is the cipher algorithms that are being used so that the researcher community can figure it out, are there any vulnerabilities with the cipher algorithm so that they can be replaced quickly. Otherwise, if there is any vulnerability with that thing, that will be there in the domain for quite long. So if you just look at a few examples of basic encryption, so you can think of something like mono alphabetic cipher that you see in this illustration, where we are replacing one letter in English alphabet with some other alphabet. Like if some, for example, if the plain text is like Bob saying, or if the Ali says something like Bob, I love you, that is converted into ciphertext, something of this kind. So here there is a one-to-one mapping between 26 letters in the English alphabet that you see it here. And one problem that you can see with this kind of simple substitution cipher is one can easily understand the patterns, and if you can look at the frequency analysis of the English words, and some characters are quite popular in a popular in the sense they appear quite widely. For example, all the vowels come quite often, and if you look at the letter E seems to be the most widely used. So even after you do the substitution as well, if you do the frequency analysis on the ciphertext, then if you see that some other letter is having highest frequency, then you can know that okay, that letter is equivalent to letter E. So like that one can able to reconstruct the plain text by looking at ciphertext with the frequency analysis and learning the patterns and other things. So it is one of the very simple encryption code that you can think of. A more advanced version of that is called n substitution ciphers. So where what you see here is there are n different cipher that are used. For example, if you take n equal to 4, we are talking about using four different substitution patterns: M1, M2, M3, and M4. And also there's something called a cyclic pattern that is defined. For example, if you assume the cycle length is of 5, that means basically what I'm talking about is if you take the same English alphabet example, I'm talking about designing these kind of substitution patterns four different times. That is, this is equivalent to saying M1. Some similarly, you can also get some other mapping of these 26 letters with some other random 26 letters. That becomes M2. Like that, generate another two more substitutions. They become M3 and M4. So when you're trying to encode data or encrypt the data, for example, if you want to encrypt, let's say, word drink, where what you do is the first letter is encrypted by looking at the substitution pattern that is available in M1. The second letter you refer to, because as I said, we have the cyclic pattern. So in this case, the pattern is having length 5, where we are talking about M1, M3, M4, M3, and M2. Basically, it says when you are trying to encrypt the plain text, in this order, you start picking the mapping letters from these four different substitution cipher that you have designed. So like that you can keep on doing it. So this has more resistance for cracking compared to the previous one. In this case, we say that the encryption key is nothing but the n different substitution cipher that you are using plus the cyclic pattern. In this case, it is M1, M3, M4, M3, and M2. And basically it also means that a key always need not to be like a some bitrate pattern. Key is something that both parties have agreed upon so that one can encrypt the message and other can decrypt the message. So key is something that is secret for you to help to decipher the communication that is exchanged. So any queries or any comments on these naive or the very early substitution cipher that are out there? Okay, so there are no comments. If you are talking about breaking these encryption schemes, in other words, trying to understand what is the plain text corresponding to the given ciphertext, we call that as cryptanalysis. There are different kinds of attacks that are possible. One of the attack that you can think of is ciphertext only attack. In this case, the attacker Trudy, she has ciphertext and she can do that frequency analysis that I talked about to try to magically figure it out what is the plain text that corresponds to this ciphertext. And again, extreme case, yeah, she can start doing all permutations that are ever possible. So it takes lots of time, but with some clever technique like statistical analysis, you can significantly cut down the time consumed for breaking these kind of substitution ciphers. And another popular attack that is possible on these encryption schemes are called known plain text attacks. In this case, Trudy has plain text corresponding to the ciphertext. For some ciphertext, she has the plain text. For example, in this case, assume that she knows what is the pairing of, let's say, these 6 different letters in the English alphabet. So by partially knowing what is the mapping between the plain text and ciphertext, so one can able to figure it out what was the substitution pattern that has been used. That is called known plain text attack. In the Second World War, to break Enigma ciphers used by German, the Allied forces used this known plain text attack, because one of the most popular thing that they came to know about is when there is nothing to report to the people that are there in the war zone, they used to say something like nothing to report. So nothing to report is your plain text, but anyway you don't send that as it is, right? You are encrypted, but many times when there is nothing to report, they are saying that that pattern is appearing, and when they were interrogating some of the soldiers that are captured, they came to know that nothing to report was one of the messages that was sent using that Enigma cipher. So it comes under known plain text attack. And compared to that, we also have a related attack called chosen plain text attack. In this case, Trudy can get ciphertext for a chosen plain text. What it basically means is that Trudy has access to this device or the software which generates ciphertext for a given plain text, and she can intelligently feed in different plain text and generate the ciphertext. She doesn't know what is the key or the substitution pattern, but she can submit as input the plain text and generate the ciphertext. By giving various types of input, the plain text as input, and getting the corresponding ciphertext, you can able to come up with another algorithm that can basically reverse engineer and figure it out what could be the plain text for any given ciphertext. So this is another way of breaking these encryption schemes. But if you look at these 3 attacks, the ciphertext only attack versus known plain text attack and the chosen plain text attack, the first one is very common. because if you look at our internet communication, we assume that anybody can eavesdrop onto the communication because one can listen to the HTTPS messages that are exchanged even though they are encrypted using different encryption algorithms. That way, uh, ciphertext only attacks are very possible, and as you see, the statistical analysis or the brute force methods are very popular to launch these kind of attacks. And on the extreme side comes the chosen plain text attack. Here you need to understand or get to know what is the actual algorithm used, including what are all the parameters that are actually applied. So this is very difficult to launch. It's not that practical. And in between comes the known plain text attack, where even if you look at our internet communication, there are some messages like these ICMP messages and even the DNS queries, which are of standard packet sizes. So one can able to try to guess what could be these kind of attacks by intelligently eavesdropping onto the communication happening out there. So by knowing the ciphertext for some plain text, one can able to try to figure it out what is the communication that is happening. So that way there are varieties of complexity that is involved for anybody to launch these three different kind of attacks. So any comments or any queries from anybody on this?
Sir, the distinction between known plaintext attack and chosen plaintext attack seems to be not so clear, sir.
Uh,
I mean, I
so
cannot get.
so you are not able to figure it out the difference between known plain text attack versus chosen plain text attack. Is that?
Yes, sir. Yes, sir.
See, in the case of known plain text attack, what I meant is Trudy somehow managed to get to know what is the plain text corresponding to some ciphertext. Let's assume that she for two different words, or let's look at this example alone. For these six letters, she has to come to know what is the mapping pattern. So that is the known plain text attack. Whereas in the case of third one, here you can assume that somehow 2D has access to the system which is generating this attack. For example, I was talking about the Second World War example of Enigma cipher, right? But I assume that Allied forces somehow managed to get hold of one of such machine that is used by German uh, soldiers to encrypt their messages. If that machine is available with Allied forces, what they can do is they can launch this chosen plain text attack. But Allied forces need not to have a machine to launch known plain text attack. As I was mentioning, they used to interrogate some of the soldiers that are caught during the war, and they were able to understand is there any standard messages that are exchanged during their communication using the Enigma cipher. They came to know that nothing to report is the one of the most commonly sent message using that machine. So that way, in the case of a non-plain text attack, we are talking about for a certain set of words, they already know what is the plain text and the ciphertext mapping. But third case, you can do any number of plain text and generate the ciphertext.
Okay, sir. So okay, sir. So I got it, sir.
So still it's not clear to you.
No, sir. It's clear now, sir.
So which one is easier? Tell me out of these two, which attack is easier to launch?
Sir, I think, sir,
Hmm.
chosen plaintext must be easier, sir. I think.
No, no. Let's assume that you are attacker, uh, where you want to break the system. You want to break a cryptographic system, and in which of these two scenarios it is easier for you to break the system? In the case of known plain text attack or chosen plain text attack?
I think, sir, chosen plaintext must be that, sir, because
Sir, I have a query here.
Mhm.
Sir, to launch a chosen plain text attack, we need access to the system as well,
Yeah,
right?
you are right. You are
Which
right. No, no. I think Ranjita, you are absolutely right. That's where I was talking about. Launching chosen plain text attack is very impractical. But having said that, once you have access to such a system or a device which is used for encryption, it is a cakewalk for the attackers to break the system.
Yes.
okay.
Sir, I think that is because they can study more patterns using
Exactly,
their
exactly.
chosen
You are
plaintext
right. But
attack.
you are right, Shubham. In the case of non-plain text, you only know one or two patterns. But in the chosen plain text, you can get any number of pattern as you want because you have the machine available, the system available with you, and you can basically you are trying to reverse engineer. But again, it is not that practical for somebody to launch chosen plain text attack compared to plain text attack.
Hello, sir.
Yeah, please go ahead.
Yeah, so if Trudy, even if managed to determine the pairing of some letters, then means you gave the example of Enigma, means it always changes the mapping of the letters. Every time we generate, it changes the mapping. Like if previously A is mapped to B, next time it's not means it will not be mapped to B any longer. So
Yeah,
every time it changes.
you are right. And also one other thing that also they were came to know. See again, this is an example that I was talking about. But again, see, Alan Turing has spent his lifetime on breaking these machines. He was treated as one of the very accomplished scientists because of his work in breaking this. If it is not that easy, yeah, anybody would have broken just like that, right? Again, I'm giving it like a very high level, superficial example. And another thing they also found out is for sending digits. Let's say if you want to send one rather than typing digit one, it is expanded at like one. That means the spelling of the one is sent, and also they were able to figure it out the patterns of using and the one, whether you use it any pairing for one time for sending one, sorry, not one, for mapping O, you use some other digit. For next time, maybe you map some other character. Next time you may do, but the length of these three-letter word remains the same, no matter what is the pairing that you use it. And also, what they found out is the people who are actually using this Enigma machine, they were also not using that. They also have some randomness that they are supposed to select some initial words, and because of laziness, they started reusing the same words as often as possible. So, because of all these things, they could able to break the system, and that led to completion of what Second World War uh, bit early compared to what everybody thought. Yeah, it is a very interesting read. Yeah, you can understand, but at a high level, this is what happens in the case of chosen plain text attack versus known plain text attack. So, any other queries?
Sir, no query, just one point. There is one more chosen ciphertext attack where
One
the
more.
attacker can
Please go ahead
chosen
again.
ciphertext attack. So in which the attacker can get the decryption algorithm and then he can decrypt certain ciphertext of his own choice.
He can decrypt certain ciphertext of his own choice.
Own choice. Yeah. So that is chosen ciphertext attack.
Yeah, that's what I was mentioning, right? In the case of chosen pair ciphertext attack, the attacker has access to the system or the tool using which he can supply the plain text. Oh, you are saying he supplies ciphertext and get back the plain text. Is that what you are saying?
Yes. Yes, sir. That is the fourth one.
Okay. You are talking about the reverse of what I said. Okay. Yeah, plain text to the ciphertext. You are talking about ciphertext to the plain text. Okay. Yeah, it is quite exciting field of research on breaking these encryption schemes. It itself is a vast subject, but yeah, here our treatment is to know that what are different kind of attacks scenarios that are possible. But many times we deal with this case. How we can make sure that your system is secure when the attacker only has access to the ciphertext only. Okay, let me move on. So let's talk about now about the symmetric key cryptography. So there are two kind of cryptographies that are out there. The most classical one is the symmetric key cryptography, where both Alice and Bob use the same key for encryption and decryption. The way you use physical keys in our real world life. So the key that you use to lock the room is the same as the key that you use to unlock the room. So that is the kind of thing. Okay. So that is called a symmetric key because there is only one key. And here key is knowing the substitution pattern in the case of monoalphabetic substitution cipher that we discussed earlier. Okay. But one major problem that you have to deal with here is how do both Bob and Alice agree on the key value? What key they should be using it? Yes, they wanted to use some secret key, but how do they agree upon this secret key? So any since half of you said that already you know this some basics of cryptography, can you somebody answer how both Alice and Bob agree upon the key value?
Sir, there are some algorithms like Diffie-Hellman using which both sides can get the same symmetric key.
Okay, so any other way other than using DP-Hellman key exchange algorithm? Is there any other thing that they can do?
Sir, there's one more way, sir, that we can use asymmetric key cryptography, and using that, sir, in the first message of their communication, we will send to Bob the key, sir, that will be used in the session, sir. And then after that, we'll use the key, sir. We'll use that session key, sir.
I think both of you are right, Anup and Shivam. One can use Diffie-Hellman symmetric key exchange protocol, or you can use a public key cryptography system where one can use RSA and other algorithms for exchanging the symmetric key. Okay, and also they can exchange this key out of band when both of them meet with each other in person. They can also exchange the key, or there could be even any other means, or they can send it over the post, or it could be anything that else that you can think of. But over a network, these are the two popular methods that are available, mechanisms for them to agree upon what is the common secret key, that is called symmetric key. And the standard that is out there that all of us use, that is based on symmetric key cryptography, is called AES, that stands for Advanced Encryption Standard. It is a replacement for data encryption standard from NIST, where NIST has this particular DS which is having 56 bit keys. Okay, and it basically processes the data in 128 bits. Basically, it is like a block cipher where it takes data of 128 bit each and does the encryption of the data. And the key length that it uses are of three different types, all the way from 128 bit to 256 bit keys that are possible for encrypting the data and decrypting the data at other side. And if you look at in terms of how challenging it is to decrypt by doing the brute force decryption, where you are trying to use each and every key combination that is possible. If it is taking 1 second on DS for decrypting, it takes these many trillion years if you are using the AES. I hope you appreciate what I meant here. Assume that somehow you caught hold of some ciphertext and you are trying to launch this brute force attack where assuming that your key length is 256. Since it is a brute force, you want to try all the way, all of the 2 to the power of 256 combinations of the keys that are possible. And if it is taking on DS 1 second to do that kind of decryption where the key length is 56 bits, if you use this 256-bit key length on by using the AES standard, it takes in the brute force method, in the worst case, it takes 149 trillion years for you to decrypt the message. So that way, the AES also relies on the computational difficulty for the attackers to decrypt these messages in brute force manner. So, see, brute force, one can always do it. There is nothing that prevents somebody from not launching the brute force attack. But the modern cryptography assumes that if one tries to use these brute force methods, it becomes practically impossible in their lifetime to decrypt the messages, since anyway they cannot decrypt in their lifetime or even in the lifetime of the earth. Nobody bothers about really launching the brute force attacks. And if you look at AES also has different modes of operation. I think they have 5 different modes. One of the simplest mode that you can think of is called electronic codebook. It is basically electronic version of the code books that were popular in 1900s, where used to have something called code books for every popular statement or a couple of words that you wanted to send. There is a short form. That means you can have 3 to 5 digit short forms are available. These are like kind of codes. It's like a code language. So rather than sending the plain text, that means if you are trying to send a letter to your friend using the postal service, rather than sending writing the letter in plain text, what you do is you use the code book, and for each word that you are writing in your letter, you identify the corresponding secret code in the code book and send it to, then you compose the message like that. That means you have the ciphertext based letter that you have written. So your friend also should have the same code book, then he can reverse engineer that. So electronic version of that is called ECB, which is available in AES. So where look at what is happening. As I was mentioning, AES is also based on block cipher, where what you do is you take plain text of certain length, and you also take a certain key which both Bob and Alicia have agreed upon by some other means. So by giving the plain text and key as input to this encryption algorithm, you generate the ciphertext. So like that, if you have a large size message, what you do is you decompose the message into like 128 bit length. For each of the 128 bits in your plain text, you have the corresponding ciphertext. Then what you do, you stitch together all this ciphertext and you compose the packets and send it to other party. So this is called ECB mode of the encryption. And at the reverse side, what you do is the opposite of that, where since the Bob is also having the same key and also has the encryption algorithm with it, it can take the ciphertext and get back the plain text. So can somebody comment on any problems with this particular mode of the AES operation?
Sir, I think it is vulnerable to maybe statistic analysis, sir. I think so, sir. I'm not sure.
So, Shubham, why did you say that it is vulnerable to statistical analysis?
So, for example, if our plain text contains our plain text will be containing normal English letters, sir, and like E, B, A, B, C, D, we can say all the letters of the alphabet, sir. So, if ciphertext, for example, consider its plain is it contains E, sir, then that will be sorry, sir. If our plain text contains E, sir, then it will be converted to ciphertext, sir, based on the key, sir. And if someone studies that, sir, then he can correlate it using statistics. He can get that this ciphertext appears many a times, sir. Because anyhow, if you're using a particular key set, then the ciphertext for E won't change, sir.
Okay, so anybody else? Can anybody else wants to add anything? Any problem that you can think of with ECB mode of AES?
Sir, not a problem, but why are we breaking them down into 128 pieces? Like, if we are using the same ECB book, why not do them all at once? Why are we breaking them and stitching them together?
Okay, so okay, I think that that comes when you look at other modes of operation, Anurag. So this is one of the five modes, and actually it is proven later that one should not be using this ECB mode because it has lots of vulnerabilities. One of the major problem that you can see here is, let's assume that the plain text is Bob, I love you. That's what Alice is saying. So look at here. Let's say assume that I have certain plain text. Using the key, I am generating the ciphertext. If I have happen to have the same plain text sent again, the ciphertext that is produced is also the same. That means the mapping between the plain text and the ciphertext is fixed. Because also, as you can see clearly, the key is fixed because we are talking about using symmetric key, which both Bob and Alice are having. Both of them are using the same key. As you see in the entire process, the key is remaining the same, and algorithm is also the same. But if it so happens that same plain text is appearing again in the communication that you are going to have, you can see to that the ciphertext also will be identical. But for any good cryptographic system, even if there is a repetition in the plain text of certain length, the ciphertext that should be produced should be entirely different. So that particular property is not maintained by this particular mode of operation. That's the reason why we don't use it. And this is called identical plain text blocks into identical ciphertext. So that's the reason why we don't use it. To address your query, Anurag, I will talk about that in the case of why it is doing something like blocks of 128 bit and all. So the way it has been done here, you can observe. You have the plain text, the encryption algorithm that is here, and the key is also here. So the key is fixed. But what is interesting thing that you are doing here is you are also adding some salt. It is also called initialization vector. What you do is before you submit your plain text to the encryption algorithm, you do XOR of your plain text with initialization vector. That means at the beginning, you randomly select some bit pattern and you do XOR of the first 128 bits with this IV, then give that as input to your encryption algorithm along with the key to generate the ciphertext. But when you are encrypting the second block of 128 bit, you don't use the same initialization vector. Rather than that, use the ciphertext that is generated here as the output of the previous encryption process while XORing the second plain text that you wanted to encrypt. So even though the key remains the same, even in this case, let's assume that this plain text and this plain text are exactly the same. That means it is equal to M and this is also equal to M. Then the ciphertext that you see here, if you call it as C1 and C2, or if it is called C and C dash, in this case C and C dash both are entirely different. That is achieved by not reusing the initialization vector, by changing the initialization vector as the output of the previous encryption operation. That way, even though there is any repetition in the plain text, the ciphertext that is produced is not identical. So that way it becomes, Shubham, you are talking about the frequency analysis. The frequency analysis won't work here in this case. As you see, you can also kind of solve and also randomized in the occurrence of different alphabets in the ciphertext. At the receiver, you do exactly the opposite. So does that make sense?
Sir, so with the key, Alice and Bob both should have the initialization vector also.
Of course, you are right. Yeah, you can see here, right, at the bottom, the Bob has ciphertext, the key, and the initialization vector. You are right. Yeah. Any comments? Any queries?
Sir, will we use the same initialization vector every time?
No, no. Again, see, that is the so why did you bring something that has to be used? When I say again means for a given session, use one initialization vector. When you change the session, you change the initialization vector.
Okay, okay.
See, it is something that Alice has to generate and pass on it to Bob. So how they can pass on the way Alice is sending key, uh, Alice also can send initialization vector using diffie-Hellman key exchange algorithm or using public key cryptography. So they can pass on both these two so that Bob can decrypt the messages.
Yeah, yes.
So, yeah, sir, actually, how are we treating the plain text here? Is it the exact length that we get, or are we adding some bits to make it that of the key length, or repeating the text to make it
No,
that
no.
of the key length?
Madhuri, what we do is when you have, let's say, message of 1000 bytes or 1000 bits, or let's say 1002 bits, or whatever it is, as any length. What you do is you divide into 128-bit length blocks, and for the last, whatever the fragment that is left up, you do the padding before you do the
Okay,
encryption. That's all. Only you have to do the padding only for the last part, not for the initial
okay,
part. Yeah.
okay, sir.
So the block size is same as the key length.
Uh, block size.
Yeah,
No,
like
no, no,
we
no, no,
are
no, 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 no. No, there is no
the
relation. Okay, I was telling, right? So look at here. The block size is 128-bit, but the key length could be any of these. But there is no relationship between these two.
okay, sir. Thank you.
So again, I am not talking about how this encryption algorithm is working. That is entirely different. You should be studying that in cryptographic courses. I'm only talking about the length of the key and length of the plain text block. Okay. How Alice and Bob can use this for encryption and decryption. More like a black box I'm talking about here. Okay. Shall we move on? Any other queries? Okay, so let me move on in that case. Okay, so a summary of this particular thing. Can you see this these three illustrations? It's very interesting illustration of how AES does the encryption in different modes. As I was mentioning, there are 5 different modes of encryption using AES standard. What you see at the middle is the electronic codebook version. So this is the classical example of what happens when you have the repetition in the patterns in the original plain text. So you wanted to do the encryption, but you failed to achieve that. So can somebody know why even after encryption, you still see a pattern more like original image in the middle, which is not possible in other 3 other different modes of AES? Can somebody guess?
Sir, you said right, for similar plain text, we get the same cipher.
Look
So,
at this penguin. All this region is yellow region, right? And let's assume that this part of the yellow region is 128-bit block, and this is also another 128-bit block. That means all the yellow regions, the white regions, and anyway, whatever the colors, these colors will be mapped into certain bit map, right? So when you do using this code book, as you see it here, when the plain text is the same, the ciphertext is the same. And because now we are rendering this using some image processing algorithm, so it will render that. And also look at all this white background, all the entire white background that you see it here, it has been uniformly mapped into certain common ciphertext. Yes, it is ciphertext, but it is revealing something that is quite interesting to note. For that reason, it has been declared that one should not be using ECB mode for cryptographic purposes. And what you see on the right hand side is the what you can get with other modes of operation. It is like as if Alice has sent something arbitrary bit pattern, because it doesn't make any sense, even though there is some sense out of what is being sent. Okay. Okay, so let's switch the gears. So far what we looked at is the symmetric key cryptography, which requires both Alice and Bob having a common secret key so that one can encrypt the message and other can decrypt the message. In the entire internet, we use AES for the encryption and decryption. So all the communication that happens over internet uses AES standard, whether you use WebEx or Zoom or Gmail or whatnot, everywhere use the AES standard for encryption and decryption of the messages. It is there pervasively in our digital communication systems. Then let's talk about what is the role of public key cryptography in the internet communication. So as you seen earlier, both Alice and Bob have to agree upon having some common key in the first place. So as some of you are telling, we can use either Diffie-Hellman key exchange algorithm, or one can also use public key cryptography to share the secret key so that they can start using the secret key for encryption and decryption. So it is quite a radical algorithm which was proposed in 1970s by Diffie-Hellman and RSA, which is Reverecht and few other researchers. And it was also known that both British researchers and US military researchers also have similar algorithms proposed in 1970s, but they were classified. They were never known in the public domain. So we came to know only what is published in the research community. So the beauty of the public cryptography is the sender and receiver need not to have a shared secret key, where we have something called public key which is known to all, and there is a secret or private key which is only known to the receiver. So how it works out is like this. Here Alice wants to send some secret message to Bob. So what Alice has to do is takes the plain text and submits to this public key encryption algorithm, which requires a key, but in this case this is the public key of the Bob. As I was mentioning, public key is the one that is known to anybody on internet, so that even Alice also knows what is the Bob's public key. So she takes the Bob's public key and encrypts the message and generates the ciphertext. After receiving the message, Bob anyway has his private key and applies the private key on this encrypted message to get back the plain text. But one interesting thing that one can think of is how Alice knows that KB plus is indeed the Bob's public key. So that is a very, very complex problem. Even though we have public key cryptography using which we have public and private keys, now Alice has the problem of knowing what is the true public key of the Bob. And since they are over internet, they cannot directly understand each other or authenticate with each other. So one technique that they can use is something called public key infrastructure that I will talk about in the next class, where we use some trusted third parties to tell that so and so is indeed the Bob's public key. That means Alice will trust some third party to get what is the Bob's true public key. But this trusted third party also has lots of trusted related issues that I will also explain you later. And there are lots of problems related to this chain of trust or web of trust that is part of the public key infrastructure. But for time being, today's class assume that Alice has the Bob's public key so that she can encrypt and Bob can decrypt using his private key. And thanks to this public key cryptography, this basically revolutionized how one can do communication in modern systems. Otherwise, symmetric key cryptography is there for 2000 years, but because this inherent problem of how one can share the keys and other things, so it was never became that as successful. But after the public key cryptography, things have become quite remarkable. So let's look at how public key cryptographic systems work. So there are a couple of requirements here. As I was mentioning, we need to have two keys. One is called public and other one is private, such that if you apply these keys in this particular manner, you can get back the plain text. And given something is the public key, it should be impossible to compute the private key. So this is very, very important because everybody knows the Bob's public key. One should not be able to figure it out what can be the private key of the Bob by looking at the public key of the Bob. Okay, that means public key should not reveal anything related to the private key. And today's class will look at one of the classical algorithm that is by Rivesh, Shamir and Adelson. This is popularly known as RSA algorithm, and people also have found some issues with this algorithm, especially with the length of the algorithm. If you look at current internet, we use the RSA algorithm with key length as 1024 bit and 2048 bits. The key sizes are becoming quite humongous and they slow down your communication process. To address that, of late what we started using is something called elliptic curve cryptography, that is also one of the public key encryption algorithm, which uses very short keys but have same properties like RSA. So that way RSA is a kind of losing its shine. But having said that, this is the one that has caught the attention of the secure communication in internet and helped us to do many things. Even though I'm saying RSA is losing shine, still we use it in a certain intelligent fashion by combining with many other things. Let's look at how one can create these public and private keys. Let's look at what is the first step here, where we have to choose the two large prime numbers. An example of that is your prime number size should be each of 1024 bits. So look at what I'm talking about here. I'm talking about prime number of size 1024 bits. Can you imagine what could be the size of this? It is, I'm talking about 2 power 10 to the 1024 bit. I mean the value could be 2 power 1024. It will be approximately translate into how much? 2 power 1024. What could be the size? Can you imagine what could be the size of this number? 2 power 1024. What is that?
300 digits approx.
300. Is that correct? Yes, it is approximately equal to 10 to the power of 300. Yeah, even more than that. So it is really very, very, very large prime number. So have you ever written a program to find prime numbers of this size? What do you think? How long it will take to find a prime number which is in the order of 10 to the power of 300? right? It takes really lots and lots of time. But anyway, for timing, assume that you have chosen two prime numbers, P and Q, where the length of each of them is equal to 1024 bits. Then you get a product of these two prime numbers that is called N. Then you find G, which is equal to P minus 1 into Q minus 1. In the step 3, what you have to do is you have to choose another number E, where E is less than N, so that it has no common factor with G. That means E and G should be relatively prime to each other. Then you have to choose another number that is called D here, such that E D minus 1 is exactly divisible by G. Okay, that means ED mod G equal to 1. Once you do that, you have N, E and D. So N comma E becomes your public key and N comma D becomes your private key. Okay, so that way we started with two large prime numbers, found N, which is nothing but product of these two large prime numbers. And then we got E, then we got D. So then we designate N comma E as the primary public key and N comma D as the private key. And if you look at how we can use these key pairs for encryption and decryption, one step for encryption that you do is when you have the message M, where M is less than N, that is the product of P and Q. So you take M to the power E, then you do modulus N. So N is the product of P and Q. So that gives you your ciphertext. At the receiver, what receiver does is he has the N comma D, then he takes D and he applies exponentiation on C and does the modulus operation with N to get back M. In other words, so this is what is happening here. The LSC is doing this operation. LSC is taking the plain text and doing the exponentiation on that with modulus operation N. Whatever the value that she is getting is the ciphertext. Once Bob receives this ciphertext, what Bob is doing is on C is again doing the exponentiation with D, which is the part of his private key. Then he is doing the modulus operation with N to get back M. So what we are doing here is called modulus arithmetic. So in modulus arithmetic, these kind of operations are happening. So a toy example is given with only 3-bit prime numbers. I'm talking about 1024-bit prime numbers and 2048-bit prime numbers, but here we have taken only 5 and 7 as the prime numbers. Then N becomes 35 and G becomes 24. Then you have to choose E such that E and G are relatively prime. In this case, 5 and 24, they don't have any common factors. So that way 5 can be designated as E. That means now you have your public key, that is 35 comma 5. Now you have to find D such that ED minus 1 is exactly divisible by G. In this case, 29 qualifies as D, because if you take 29 into 5, you look at 29 into 5, that is 145, minus 1, 144. That is exactly divisible by 24. So if we take a toy example where let's assume that you have an 8-bit message. See, at the end of the day, whether it is images or the videos or whatnot, it becomes a binary bit stream. So you chunk into 128 bits in general, but in this case, assume that you are having taken messages of length 8 bits. So here the message equal to 12. When it is converted into binary pattern, it becomes 1100. So when you apply the exponentiation on E, that is what you are doing is 12 to the power 5. That is this number. When you do modulus with 35, you will get 17 as the thing. That means Alice wants to send 12, but when it is converted into ciphertext, it became 17. Bob receives 17, which is the ciphertext, does exponentiation on 17 with 29, that is D. That means 17 to the power 29, which is really a large number. On that you do the modulus 35, it magically becomes 12. So that's how the RSA algorithm works. So any comments or any queries on this, how this is working out? It is like basically it is a number theory. It is a number theory how we can do the exponentiation and do all that. But so this is the algorithm they have proposed. So it looks very simple to understand, but again it has all the sound properties for to be making the internet communication secure. So any queries on how the key pairs are generated and how the toy example is working out? Any queries from anybody? Okay, so if there are no queries, let me talk about why RSA is secure. As I was mentioning, everybody knows Bob's public key. In that we have n comma e. The question is how hard it is for anybody to find out D, which is part of the private key of the Bob, that is n comma D. So what we are talking about is finding the factors of n without knowing the two factors p and q. That means in the public key we have n. So if you recall, n is obtained by multiplying two large prime numbers. So whoever has the Bob's public key has the value of n, but is it possible for somebody who is having the value of n to find out which two prime numbers resulted in this large product of n? Since I'm talking about very large prime numbers, which is of order of 1024 bits and 2048 bits, the prime factorization of these large numbers is really hard, and RSA is working on the principle that even with the modern supercomputers, it takes a large amount of the time for somebody to find the factors. That means the prime factorization is still very challenging problem. So it is very impossible to find out what is p and q given n. So recall here, so n is known to everybody, and if somebody can magically get some pair of p and q that gives you n, they can actually do some permutation on these values to figure it out what could be the d. Of course there could multiple such d's that are possible, but the search space becomes very small once you do the factorization of this large number. So the current RSA relies on that. This prime factorization is really hard, especially with the large size numbers. That's why we use very large numbers as the prime numbers. So current RSA key sizes that we use are of 2048 bits. And if you look at how we use RSA in practice, I was mentioning earlier as Anurag, yeah, go ahead.
Sure. Getting P and Q is also hard, right? Or is generating prime factors easy? Because when we generate a 1024-bit number, we need to know if it is prime or not. That means we need to factorize it. P and Q itself.
Tell me again, Anurag, what you are saying is
how do we get P and Q? Suppose I give some number to you and say that it is a 1024-bit number. How do we know that it is a prime number? We need to factorize it, right?
Okay. What you are saying is finding a large prime number itself is a problem. That's what you are saying.
Yeah, yes, sir.
Yeah, you are right. You are yeah. Once I give a number, whether it is a prime number or not, that itself is a big problem. And yeah, in addition to that, once I give some number n, which pair of prime numbers give this as that is itself is another problem.
Yes, sir. But how do we get P and Q? Like, do we get them?
No, see now, I think, hello?
Yes, sir.
See, the P and Q, so what you are talking about is how do you generate these two prime numbers P and Q, right? That's what you are asking.
Yes, sir.
See, generation of the prime numbers, large prime numbers is already done in the literature, and it is there. I think if maybe somebody can answer. I have not done really this part. Maybe somebody can. So there, finding large prime numbers is possible in definite amount of the time. It is not going to take extremely large time value.
It is 1024 bits is each prime. So when then n will be actually 1024 bits into 1024 bit, which will be even larger, right? So maybe its factorization to find prime factors is taking much more time. So it is not like n. Hello, am I audible? Hello.
So I got I'm able to hear you, Ranjita. Basically, what you are saying is if the length of P and Q is of 1024 bits, you are saying the length of N is the 2048 bits. That's what you are saying, right?
Yeah, that would be even larger, right?
Yeah, I agree. I agree.
Yeah,
Yeah.
definitely. So
Yeah.
I think
See, I think what Anurag is asking is, see, the I think he is also agreeing that prime factorization is a large problem. I think his question is how easy for somebody to generate these large prime numbers of size 1024 bits or 2048 bits. Right, Anurag? That's what you are asking, isn't it?
Yes, sir. Yes.
So can I think those who have done the course on cryptology, can you guys answer? Even I wanted to know.
Hello, sir.
Sir, we won't be going checking each number if like one is prime, two is prime, like that. So until 10, 2 or 10, 24, right? Like C of resources is there, we just directly uh, go and O off, and we don't check each and every number to see if it's prime or not.
No, if that is the case, then we would also be able to figure out 2048 bits also easy, like relatively easy, right? If we use Eratosthenes. I don't think Eratosthenes is also viable for checking if P is.
sir, the basic difference is one is factorizing n, the other is for making sure whether a number is prime or not, there is some method like sieve method or something which can be done in a
Polynomial time.
faster way. Yeah.
Are
Actually,
near
Yeah.
polynomial.
actually we use sieve of Eratosthenes, sir. So in that we can do n to the power half or root n times, sir.
And root n is very large in this case, approximately 10 power 150. It is not small.
Sir, excuse me.
Sir, so the Miller-Rabin, sir, what happens is that computer generates any any random number of what to 124 bits. Then, sir, it does some test like a Miller-Rabin primality test to check whether it is a prime or not, sir.
So what you are saying is you randomly generate some 1024 bit number and you check whether it's a prime number or not. If not, maybe you start checking its neighborhood numbers or some other random numbers till you find some large number. That's what you are saying.
Yes, sir. Actually, as I have read or as I have listened that that algorithm does not goes on for infinity or some. It has
Yeah,
some
yeah, it should
stopping
not
point.
go on. See, if you look at in all the communication that you use, see, Alice has to generate, or the Bob has to generate this key pair, right? And in this, in general, what happens is, say, also, I guess you guys are using our WireGuard VPN, isn't it? All of you have generated public and private key pair, and you have shared your public key to our computer center team so that you are able to have successfully installed WireGuard and able to access to our thing. And if you recall, the time that has taken for you to generate your public and private key pair, which involves you in finding n comma e n comma d, which all happened in a very fast manner. I think what I've anyway, I have not done any of this from my side, but I believe I think as some of you are pointing it out, so there are intelligent ways for you to quickly determine find out P and Q so that you can get started in finding the public and private key pairs. So, but what is still a open problem is factorization of a such large number. If P and Q are of length 1024 bits, N is could be of length maximum up to 2048 bits. Getting the factorization of such large prime numbers is going to be really so time consuming.
I think.
Hello?
Yes, I'm saying that is it one type thing.
Madhuri, your voice is breaking. I'm unable to hear you. So, Madhuri, are you still talking? I'm unable to hear you. What about others? Are you able to hear me?
Sir.
I was saying it is not in a one-time. Okay. Oh, you are asking about generation of the public and private key pair. Yeah, in general, it is one time. As a user or as a system, you require only one public and private key pair. Yeah, you use, for example, when you're doing SSH for a remote login, there also you are generating a public and private key pairs. Similarly, when you're using our wildcard VPN, then also, yeah, it is a one-time thing. But I think I see in the chart window also, I think people are talking about there are algorithms that help you to find prime numbers in polynomial time. But what is still we don't have in polynomial time is factorization of a large prime number. Sorry, large number. We don't know when. See, n could be prime number or not. That is secondary. But we are not talking about that. A certain number is given. We want to find its factors. So that itself is still a time-consuming process. So Miller-Robin is currently industry standard as per link above. What is that Miller? It is a probabilistic algorithm for finding whether a given number is prime number or not.
Like there is some error rate and we keep applying iterations until it's some acceptable error rate.
Okay. Fine. And I think we are running late. And let me go back. Okay. So I was just mentioning that in modern communication systems, the way you do is first you use RSA to secretly share the session key between Alice and Bob so that rest of the communication can happen using the symmetric key, whereas the RSA is only to share the secret key. The reason why we have to do this kind of thing is RSA, because of the exponentiation that is involved in encryption and decryption process, it is quite time consuming compared to using DES or other symmetric cryptographic algorithm. For example, if the DES is taking or if you compare RSA versus DES for encryption, DES is 100 times faster than RSA. Okay. For that reason, we use public key cryptography to establish the secure session. And once you establish the secure session, then you share the symmetric key. Then you can start using that. for encrypting and decrypting the data. That way your data communication won't get slowed down because of the exponentiation that is involved in encrypting and decrypting the messages as part of the RSA. So only share only the passwords for the authentication purposes, share the secret keys for before you started encrypting and decrypting the data using RSA. That way RSA is quite remarkable even though it is quite expensive in practice, and it makes symmetric cryptography to do its job much better over unencrypted channels. So let me stop it here, and yeah, we'll continue in the next class about digital signatures and message digest, how they will help you in addressing message integrity and other aspect of secure communication. So far what we discussed in today's class is both symmetric cryptography and asymmetric key cryptography, which basically gives you the confidentiality of the communication. So we'll talk about the data integrity in the following class. So any other queries from anybody? I can wait for a couple of minutes if somebody wants to have any questions answered related to today's class or other.
Sir, hello, sir.
Yeah, go ahead.
Sir, although we cannot now complete, cannot do statistical analysis, we can do a source and plain text attack on RSA, right?
You can do yeah. In fact, I was saying right. So that in fact that is very popular. See, I will also tell you. I will also share you later. There were lots of research papers. They talk about by looking at encrypted videos that you watched. They will tell you which movie that you watched. That is a kind of a chosen plain text, because here you know the length of the basically the the streaming quality and the message length and what is the streaming platform that you use. That means a lot of metadata also is going to help you to understand what is happening. So the current state of art is how you can understand what is happening by looking at the encrypted messages.
Okay, yeah, yes.
Yeah, you are right. There still, unfortunately, we are sharing the same channel, and yeah, with a lot of metadata. And as I was mentioning, right, one can also look at, see, if you look at the DNS queries, the DNS queries that your laptop generates are of standard length. In general, DNS go over plain text, but even when you're talking about the secure DNS, there also after encryption, the message sizes that are generated are of standard size. So one can look at all the standard messages that are out there and can able to also, in a way, if you look at internet headers, I will talk about this later. The IP layer headers and the transport layer headers go in plain text. That way, the receiver, the eavesdropper knows whom you are talking with, and that way they get lots of metadata that, along with standard messages that exchanged in internet, can help them to know certain plain text for the cipher. The cipher text and the plain text combinations. With that, it is possible to, yeah, able to launch some kind of breaking attacks.
Okay, thank you.
Sir, the public key of a person is same for everyone. Sir.
No. Each user has its own public key.
Yes, sir. I mean, for the particular user, everyone can be seeing only a same public key. Right?
Yes, each user has, let's say I have one public key that I advertises over internet stating that, okay, in fact, anyway, I have not done it. Maybe I should do it because I'm teaching this course.
Yes.
You can see some people when you visit their home pages, they also put their public key.
So
Do you
does
know
that
what?
mean they will be having the same private key for every received message? Like we see some
No,
message
no.
like end-to-end encryption.
Yeah, it is for end-to-end
So
encryption.
it
Let's say
means that private key should be different for each messaging or chatting with
no,
different
no,
person.
no, 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 no. Okay, I think Vamsi, let's talk about two things one after other.
Yes.
Each user has one key pair, that is public and private key. Public key is the one that is basically public key is like your house address that you advertise to everybody on internet. Like a private key is like the key that you have for it your home. That way letter comes to your home, but only you have the key to open something of that you can think of. So that way whoever wants to communicate in a secure fashion to you, they can use your private key, sorry, your public key, and encrypt the message and send it to you. After receiving the message, since you have your own private key, you can decrypt that ciphertext and understand what is the content of the message. So that is what possible. But what I'm talking about in the internet is internet we don't use public private key in this fashion. The way you use public private keys in the internet is I use like if we take a communication between Alice and Bob. What Alice and Bob do is I don't know whether do I have an example. Let me. Or maybe just hold on. So are you able to see my screen?
Yes, sir.
So we have Alice and Bob. So what first Alice has to do is the step one is getting the public key of the Bob. Okay, so assume that somehow Alice has the public key of the Bob. Okay, so then what Alice is going to do after getting, let's assume that this is the case where I will write Alice has this one. Okay, so Alice has this key, which is the Bob's public key. So then what Alice does is case. So Alice generates some session key. Let's say they are using like AES standard. So assume that this public key is based on RSA. So what Alice does is Alice encrypt the session key. I'll write Alice encrypt session key Bob's public key. So can you tell me what happens next? Can you guess what happens next? So what Bob will do now?
He will use his private key to decrypt this.
Yeah, Bob uses private key. This is based on RSA, okay?
Yes, sir.
To know the session key. So once now look at what happened. Now what happened? Oops. Now what happened at this stage? Both Alice and Bob, both of them are having session key. Now encrypt the message using KS. The Bob does the decrypt the message, decrypt the, or let's call it as C. Decrypt them using KS. So look at what I'm talking about here, Vamsi. Is that clear?
Yes.
Yes, it is possible for Alice and Bob to directly use RSA, or in other words, the public key cryptography, to encrypt and decrypt the messages using the combination of public and private key pairs. Because of the exponentiation that is involved in RSA, in practice, what we do is we use RSA very rarely, only to establish session keys. Once the session keys are established, because in this case what happened, Alice has generated some session key and shared with Bob. After they have exchanged the session keys, they can start encrypting and decrypting their messages using AES, because symmetric key is much faster compared to RSA or other
Alright.
things.
So my doubt is that for a
Hmm.
particular user, will he be having same private key with for every other person, or will it be different for each person?
And tell me again, Mumsi.
Like for with respect to a person B, will he be having the same private key for C and D, or will it be different for each of them?
See, private key
Like
is personal, right? Private key is something that is like, look at Alice and Bob. Explain with respect to Alice and Bob. Okay, maybe we have
we
let's
need a
say
third person.
let's call it as yeah, we have okay. So we have something like X. Some other person is also there. Okay, now explain.
Like if A is sending message to B and X is sending message to B,
A
will
is
the
sending
private
to,
key
okay, you are talking about A is sending to B and X is
and
sending to B. Hmm.
yes, sir. Will the private key for B be same in both cases, or will it be different?
Yes. See, when X wants to share some secret key with B, because see, X also wants to have a secret communication with B, right? For
Yes,
that,
sir.
what X has to do, X has to encrypt the session key with Bob's public key.
Yes, sir.
Okay, for example, uh, let's say X is there, right? Okay, this guy wants to have another session. Let's call it KS2, let's call it as. So what in this case what happens is they exchange X and B exchange this new session key again using the RSA. In that case, what X does is X encrypt the message, in this case the session key, using the Bob's public key.
Yes, sir.
So after receiving the message, what Bob does is Bob applies this decryption algorithm, and by using its private key. In other words, Bob has only one private key with it. Whoever wants to communicate with Bob, they have to use the Bob's public key.
Okay. Yes, sir.
Okay, so in other words, you can assume that each user has their public and
Secret.
private key combinations, and everybody advertises their public key. You can advertise on your homepage, you can advertise on your LinkedIn, Facebook, or you can also advertise on this public key infrastructure. So there are lots of means by which one can advertise. And let's say you are interested in having everybody communicating with you secretly. You generate some public key and you put it on your home page and ask everybody to send messages by encrypting using your public key, so that nobody can read without having your private key.
Yes,
Okay.
sir. I understood.
Okay, so any other queries anybody having?
Sir, in the slide you mentioned DES is faster than AES, right? The symmetric one.
No, tell me again. B.
DES is faster than AES, like 100 times faster
No, no,
or
no, no, no,
something
no,
like
no. I was saying oops, I was saying DS is faster RSA. In other words, basically the point I was trying to make is symmetric key based encryption and decryption are faster compared to asymmetric key based encryption and decryption. So because of this reason, we will use asymmetric key only when it is absolutely necessary for exchanging the session keys. After that, we'll start using the symmetric key because they are quite faster for doing the encryption and decryption because they don't involve any exponentiation like what you see in RSA. Also, one of the weakness or the limitations of RSA is the exponentiation that is out there, and also the large key size because it is relying on the factorization of the large numbers. That has been kind of addressed when you look at this elliptic curve cryptography. That is a recent standard. So this particular ECC has kind of taken over RSA in terms of the asymmetric key cryptography. But even after using ECC, you only use ECC to generate or to exchange the secret keys, I mean the session keys, which is the symmetric key. After that, you start using AES. Because this is the default standard for all communications that are out there. Does that make sense, Harsha?
Yes, sir.
Okay, let me go back to the slide, see what is written out there. So look at DES is at least 100 times faster than RSA, not AES. Of course, it may be faster than AES because see, DES is only 56 bit, whereas AES now we are talking about even 512 bits as well. But having said that, DS is already broken, and in no time one can break messages that are encrypted using DES and all. So one should be using only AES with either RSA or elliptic curve cryptography, which is based on finite field theory and other things. So in summary, you can look at here. Both Alice and Bob use RSA to exchange a common symmetric key, that is KS. Once both of them have KS, they start using KS for secure communication. That way, asymmetric cryptography is only to exchange KS. Afterwards, we still use the symmetric. That way, we are using both symmetric key cryptography and asymmetric key cryptography in modern communication systems. So any queries? Anybody having? I don't see anything in chat window. Sir, is it audible? Ranjita, are you asking anything? Still, I see there are 30 students patiently listening. So you guys tell me if you have any other queries. Yeah, I'm happy to spend some more time. I think that way Thursday class is beneficial because I am free and you are free. So we can have any discussions, open-ended discussion on Thursday's class. So those who are having anything, you can feel free to ask me after Thursday's class. So
Sir, DES is no longer secure, no sir? That's
yeah,
what you...
yes.
Yes, sir.
So all of us use only AES in the case of symmetric key cryptography, but in the case of asymmetric cryptography, we have the choice of using RSA or elliptic curve cryptography. So nowadays, I think if you look at the modern HTTPS, where we are talking about the TLS 1.3 standard, so they kind of deprecated RSA and they started relying more and more on elliptic cryptography because the key sizes are small. They are not like 1024 and 2048 bits. They are just like 256 or 512 bits only. But they are as stronger as RSA. Okay, guys, any other queries? I think we are touching 6 o'clock. If no queries, I'll take the break. Okay, shall I stop? At least one of you should say yes. Otherwise, I will be here only.
Yes, sir. Thank you.
Okay, guys. So, yeah, let's meet again on Monday and continue the discussion.